All right, we'll go ahead and get started. Welcome once again, everyone, and thank you all for joining us for our September 2024 Eversight webinar on applications of artificial intelligence in cornea. My name is Colin Ross. I'm Vice President of Partner Relations and Global Development for Eversight, and we are grateful to have you all with us. A few general notes before we get started. This webinar and all of our webinars are recorded and they're available on demand at the Eversight website, which is eversightvision.org. Please keep an eye out for our future webinars. You can find information on those there as well. Our next one in the series will be on November 13th, featuring Jill Maher, speaking on the topic of succession planning and physician recruitment. Please also note that all attendees will be muted throughout this evening's webinar, but we absolutely encourage you to ask questions using the Q&A panel, and we will be thrilled to address those questions at the end. Now it is my great pleasure to introduce our speaker for this evening, Dr. Travis Redd, who, as I mentioned, will be speaking to us on the topic of the uses of AI in cornea. Dr. Redd is Assistant Professor of Ophthalmology in the School of Medicine at Oregon Health and Science University, where he also completed his medical school training, residency, and a Master of Public Health degree. Dr. Redd completed his fellowship in cornea and external eye disease at the Francis I. Proctor Foundation and University of California, San Francisco. He has particular expertise in infectious and inflammatory diseases of the eye, and his current research interests include the application of emerging technologies to reduce the burden of corneal blindness both in the United States and internationally. We are very grateful to Dr. Redd for sharing his insights and expertise with us on this very timely and important topic. And so, Dr. Redd, I would invite you to take the floor.
All right. Thank you very much, Colin, for that kind introduction. Hello, everyone. Appreciate you giving the opportunity to talk about AI in the management of corneal disease. As Colin mentioned, I'm hoping we'll be able to have the chance to have a rich discussion on this topic. As Colin mentioned, I'm a cornea specialist and a data scientist at the KCI Institute in Portland, Oregon. And I'm just going to give a broad sort of overview of this topic. As I'm sure many of you are aware, it's constantly changing. AI is, always in the news due to the rapid advancement of this technology. So a lot of what I will say today was probably going to be out of date in the near future, but hopefully it will give you a broad sort of overview and understanding of how AI is currently being investigated for applications in cornea, and some thoughts on sort of future directions and areas that we need to focus to move toward meaningful clinical implementation of this technology. So a few disclosures. Some of the research that I'll describe that my own group has done is funded by the NIH, National Eye Institute here in the US, as well as Research to Prevent Blindness, Collins Medical Trust, and Malcolm M. Marquis Endowed Fund for Innovation, but I have no financial conflicts of interest. So general outline for what I'm going to go over today. First, we'll just discuss some background and terminology on AI, and particularly AI in medicine, just to make sure we're all sort of on the same page and using the same vocabulary. Secondly, I'll go over some of the current applications of AI in cornea and the most up-to-date research in this area. Then we'll discuss some barriers to how we can effectively implement this technology in clinical practice and some future directions for how to hopefully overcome those barriers. So again, to start with, it's a bit of there's a lot of jargon surrounding AI currently. So just to kind of go over some of the terminology here. AI, or artificial intelligence, has actually been around for a long time. You may have only been hearing about it over the last 10 years or so, as I said, it becomes more commonly discussed in popular culture. But it's been around since at least the 1950s. Alan Turing is generally considered sort of the original father of AI, for lack of a better term. And essentially AI just means developing software or machines that are capable of performing tasks that are traditionally thought of as requiring intelligence. So it's a very broad definition for the first several decades of AI research that essentially meant developing really complex programs and essentially presenting algorithms to address complex situations. So, for example, developing an AI model to play chess or various other um, uh, board games or video games, perform other complex tasks, essentially required, again, very complex, sort of nested algorithmic approaches to say, if this thing happens, do this. And as you can imagine, as tasks become increasingly complex, the sort of branching logic that's required to successfully perform those tasks becomes prohibitively complex. So around the 1980s, 1990s, machine learning came along to sort of address this problem. And it's a pretty fundamental paradigm shift from more traditional artificial intelligence approaches to essentially allow learning algorithms to learn to perform these complex tasks without being explicitly programmed. So machine learning engineers don't necessarily give a set of instructions for how to perform a task. They instead present as much data as possible to a model to allow it to learn how to perform those tasks by being iteratively exposed to data. So Arthur Samuel sort of famously described this as giving computers the ability to learn without being specifically programmed. So the learning algorithm or the program learns to optimize some performance criterion or perform some task by being exposed to data. So that's the sort of experience that the model accrues. And again, learns from that experience, its exposure to data over and over again to be able to perform those tasks. And then more recently, we've seen the advent of deep learning. That's really only in the past decade to 15 years or so. And that's really revolutionized a sort of subset of machine learning that's specific to unstructured data. So, traditional machine learning techniques like random forest models or support vector machines or even logistic regression or linear regression are really good, but particularly at interpreting what's called structured data. So you can think of like traditional sort of tabular data or data that would fit into an Excel spreadsheet. That's structured data. Unstructured data, which is what we tend to deal with quite a bit more in medicine and ophthalmology specifically, is things like images, text, speech, data that doesn't really fit into a spreadsheet. And so if you're going to develop an artificial intelligence model to interpret unstructured data like that, it needs to be able to sort of extract meaningful features from that raw data. And again, that's really what deep learning is particularly adept at doing. So this essentially all deep learning utilizes an underlying framework called a neural network. At least in popular media, you'll often hear this described as machines that are designed to learn in the same way that humans do, so sort of modeled on the human brain. I think that's not really an accurate characterization of what a neural network is, particularly because we don't really even understand how the human brain learns things or functions. So we're not very well equipped to design an artificial version of the human brain. But essentially what deep learning is layers of these neural networks, or essentially learning nodes that are able to learn more and more complex representations of unstructured data by feeding that data through successive layers. I'll talk about that in a bit more detail momentarily. But again, the real innovation with deep learning is that these models are now end-to-end. So instead of feeding in structured data where you can, you specify the age or the exposures that a person has experienced, their blood pressure, etc., specifying all of that structured sort of feature level information to the model, and then teaching it through machine learning to extract meaningful information and make useful predictions. Instead, we're just feeding raw data, in our case, mostly images, and the model has to learn those features itself. And so that's what's meant by this term end-to-end. This model takes raw inputs, produces a raw output. And that's really, again, necessary for fields like computer vision, where we're trying to do interpretation of images or video, or other image-based data. Um, the the benefits and the drawbacks of that are, again, it's that's really the only way that you can interpret unstructured data is with an end-to-end model. But the downside is, there's less of a human in the loop, right? So that makes the explainability of what these models are actually learning uh, quite a bit lower. So it's harder to understand how a deep learning model is using the information that we present to it in order to make its predictions. And that has implications that we'll discuss a little bit later. And just to put in a plug for some of my colleagues here in Portland, Oregon, wrote an article several years ago now, I guess 2019, going over a lot of this jargon and sort of explaining the terminology that's used in this field. So it's a great read for anyone who's interested. So again, just more sort of a visual comparison of these different approaches to artificial intelligence. So over here on the left, you have a traditional logistic regression model. So we're taking clinical data. There's manual risk factor extraction, or you can also call that feature extraction, where again, the clinician or the researcher is determining, is the patient older or younger than 75? What's their gender or sex? What other risk factors do they have? Feeding all that information into a model, and then the model essentially just weighs each of those features, combines them, basically produces a linear combination of all that information to come up with a prediction. A standard feed-forward neural network actually has a very similar architecture on the sort of micro level, but stacks those layers, essentially just logistic regression layers or neural network layers, stacks them consecutively so that you can learn more and more complex representations of that low-level data. And in the computer vision world, what really sort of revolutionized deep learning for computer vision was the advent of something called a convolutional neural network, which essentially just means you're taking these convolutional filters, these little 3x3 or 5x5 filters, passing them over an image to interpret a group of pixels to come up with these features of the image. And so in a deep learning framework, you do that by first looking for low-level features like determining edges, patterns that are oriented horizontally or vertically or diagonally, etc. And then just successively doing that over and over, combining the results of those lower level features to abstract higher and higher level features. And with enough layers and enough parameters, you can eventually learn to recognize really complex shapes and lots of different representations of those shapes, including, recognizing faces or objects or other more complex features of images. The ILS VRC is a sort of annual competition, worldwide competition in computer vision that's kind of served as a benchmark for how well these computer vision models are performing over time. And AlexNet was really the first big deep CNN to be to participate in this competition, which essentially involves trying to recognize 1,000 different objects or classifications within this really large data set of images that are collected from, again, all over the world. And AlexNet really blew the competition out of the water with accuracy in a range of about 60% for identifying those the top 1% most common classes in the data set. And then over the years, you can see the performance has just continued to get better and better. So now we're over 90% top 1 accuracy in image classification. And again, that's really largely due to the advent of deep convolutional neural networks over this time. Here you're seeing a plot of the number of parameters of these models, which are also exponentially increasing over time. So that's part of the reason that these models are able to perform so well is that they have a huge number of parameters and they have many, many layers. So the depth of these models continues to increase, and that just allows them to, again, extract more and more complex representations of unstructured image data. The downside of that increasing number of parameters is that these models become increasingly, quote unquote, data hungry. So in order to train a model with many millions or billions of parameters, you need larger and larger data sets to be able to do that, at least to be able to train models that are able to learn generalizable information. So not just memorize the test set, or excuse me, the training set, but to learn meaningful representations that will also translate outside of the training set so that it can, interpret images that it's never seen before. So in medicine specifically, there are kind of three different paradigms for how AI can be implemented and incorporated into clinical care. So one is the sort of assistive approach. And that essentially means designing models that are able to provide useful information to a clinician to inform more complex decision making. So one example is Mia Woodward's group at the University of Michigan has done a lot of great work on corneal ulcers and sort of biomarker quantification. So being able to develop models that are able to automatically segment images of corneal ulcers and determine, what is the exact size or area of the epithelial defect, the corneal infiltrate, hypopyon, et cetera, and really quantify those biomarkers, which is, I'm sure the cornea specialists in the audience will recognize immediately, is really useful for monitoring progression over time and response to treatment, especially if you have multiple different providers who are seeing a patient, to be able to have some sort of objective measure of the overall disease severity and sort of manifest in these biomarkers is very useful. There are also augmentative implementations, and you can think of this as really a model that's working in parallel with a clinician or a practitioner of some kind to sort of abstract more complex information, but not to function on its own without any support from the clinician. So in the case of corneal ulcers, that could be something like a model that's trained to take an image of a corneal ulcer and give you an indication of what type of ulcer that might be. So we'll talk about this in a little bit more detail momentarily, but sort of subclassifying into bacterial, fungal, viral, or protozoal ulcers. That, of course, has implications for treatment, and it's a challenging task that requires a fair amount of expertise. And so in this situation, you might be able to implement a model like this at the point of care so that clinicians could take a photo and then, again, have some indication of what type of ulcer they might be dealing with, which might help them inform their treatment regimen moving forward. And then lastly, you have autonomous implementations of artificial intelligence. And probably the best example of this is in the diabetic retinopathy world. IDX-DR, which some of you may be familiar with, was the first FDA-authorized AI model in ophthalmology, and it's used for automated screening of diabetic retinopathy. So most of these autonomous implementations are going to be for screening purposes, basically trying to reduce the size or the pool of patients who need an in-depth examination by an expert by identifying patients who are at high risk and getting them plugged in with the care that they need. So as we move through the specific sort of potential implementations or areas of cornea where AI has been most sort of intensively investigated, keep in mind these three different sort of approaches to how you can implement AI because there are significant implementation or implications for the type of research that needs to be done to inform the development of these types of models. So to go into more specifics on, again, sort of areas of cornea where a lot of research has been done relating to AI specifically. Infectious keratitis, I'm a little bit biased because this is the area that I tend to focus on the most, but a lot of great research has been done by other groups as well. And models have been developed to interpret a lot of different imaging modalities as well, which is interesting. So there are models by this case published by Z et al. They developed convolutional neural networks to automatically interpret confocal microscopy images, and reported quite good accuracy at identifying, filamentous fungal keratitis as represented in this bottom left panel here. And a number of other groups have also looked at using confocal for automated detection of acanthamoeba and other forms of infection. So that's more of sort of an augmentative implementation of AI, I would say. On the more autonomous side, Mo Tiwari et al. Published a couple of years ago a model trained to identify whether or not a corneal ulcer is present and also differentiate active infection from a healed scar. Which could actually have some implementations in an augmentative capacity, but also potentially an autonomous capacity to, again, sort of screen for corneal ulcers, identify patients who need more in-depth and emergent care. And that was done, that model was trained using slit lamp photographs of corneal ulcers, as you can see here. Here are heat maps, which you'll see often if you look through the AI literature, particularly in medicine. Essentially, what this is doing, if you're using a heat map or a GradCam heat map for a convolutional neural network, essentially what this is showing is those later layers or the very end of the model, what portions of the image are activating those later layers the most strongly. So it's sort of an indirect way to try and get an idea of what portion of the image is the model paying the most attention to. And these are just those same slit lamp images with the heat map superimposed. So you can see, the model tends to pay the most attention to the area of infiltrate or scar, which is, as clinicians, what we would expect it to do. And interestingly, again, this is end-to-end model training. So there's no sort of a priori human annotation to suggest to the model, hey, you should pay attention to this portion of the image. It just learns that that's the most important part of the image for this particular classification task, based on being exposed to a large amount of data to learn those associations. And then here, again, my own group has done some work in this area, specifically on what I mentioned earlier, trying to subclassify types of corneal ulcers, again, sort of an augmentative implementation of AI. And our group and others have shown that, convolutional neural networks are actually quite good at doing this. So in this case, if you take a collection of corneal ulcers from South India and train several different convolutional neural networks to classify them into bacterial and fungal keratitis, the models have an area under the ROC curve of about 0.85. And sorry, just to orient you here, you'll see quite a few ROC curves through the rest of this talk. That stands for receiver operating curve, and essentially gives you an idea of the balance between the sensitivity and specificity of any prediction model, and how that fluctuates as you change the threshold that you use. So these models will output a prediction anywhere between 0 and 1, and you can set the threshold anywhere you like to sort of say, any prediction above this threshold is a positive, anything below is a negative. The ROC curve is a nice sort of quantitative way to describe how well the model is able to discriminate between two different classes. And so essentially a very good performing model will have an ROC curve that's pushed up toward this top left corner. And the area under the ROC curve just gives you a single value to kind of quantify the model's performance. Area under the ROC curve of 0.5 would just mean essentially random guessing, so a model that really has no discriminative capacity. And an area under the ROC curve of 1 would be a perfect classifier. So again, the computer vision models trained to perform binary classification of bacterial and fungal corneal ulcers have an area under the ROC curve about 0.84 or 0.85. And our expert humans who we had perform this same task, including 66 cornea specialists from all over the world, had an average area under the ROC curve about 0.876. So these computer vision models are already performing about as well as expert cornea specialists at performing this task. Keratoconus is another area where there's been a lot of interest and excitement in trying to apply AI. There's a great Cochrane review published just last year reviewing the many studies. I think they found 63 different studies uh, involving developing AI models for detection of keratoconus. Overall, their findings were, in general, these models are very good at detecting manifest keratoconus. So you can see here if 1,000 people were tested, 30 people with keratoconus would be correctly identified and none would be missed. So that's a perfect sensitivity. And of the remaining 970 people, only 17 would be wrongly referred. Those 17 would undergo some unnecessary additional testing, but generally not anything invasive. So it's a very good screening test specifically for manifest keratoconus. When you start looking at subclinical or forme fruste keratoconus, it becomes much more challenging, which I think as clinicians, we also experience that difficulty. So as of right now, the models, I'd say in general, are not great at detecting preclinical keratoconus. But manifest keratoconus, they are quite good. And I should say almost all of these studies were using tomography data to make these predictions. Refractive surgery is another interesting area where AI has been evaluated. Not quite as many studies as for keratoconus or infectious keratitis, but still certainly a lot of interest. This group trained a model to detect post-refractive ectasia using pre-surgery tomography. And they developed models that actually, as you can see here, performed really quite well. But I think still more work to be done. These are still studies with relatively small sample sizes, but still promising results in the preliminary data. A number of models have also been trained for various applications in corneal transplantation. So this study by Hayashi et al. Interpreted OCT scans of post-surgery DMEK graft patients. And they were able to train a convolutional neural network that performed very well at detecting not only detecting detachment, but also predicting the need for rebubbling with an area under the RLC curve of about 0.888, which is quite good. And a number of other studies have also looked at potential applications in other forms of corneal transplantation like DSEK and PKP. And then also sort of close to my heart is trachoma. And several studies have looked at trying to develop automated detection models for trachoma with quite good success. So this studies was just recently published by Ashlyn Joy in the Cornea Journal. And describes a deep convolutional neural network that had near perfect performance at identifying TF or trachomatous inflammation follicular based on photographs of everted conjunctiva. And this, I think, would fall more into that category of autonomous implementation. So, technology like this could potentially be implemented for trachoma screening programs, potentially be used to determine community-level prevalence of trachoma and eventually guide mass distribution of azithromycin campaigns. So again, just to quickly review, again, a lot of potential sort of areas or types of implementation of AI in cornea, but in general, they mostly fall into either classification tasks, which can mean either detecting a condition or automated diagnosis, or subclassifying different types of diagnoses. We talked a little bit about biomarker quantification and phenotyping with Dr. Woodward's work at University of Michigan. Prognostication is another really interesting area that kind of falls into this biomarker quantification category as well. But training models using longitudinal data to try and predict future outcomes is another area that I think is particularly exciting. And as I mentioned, has also been investigated in refractive surgery screening and keratoconus monitoring for progression, things like that. And then community level screening, as has already been implemented in diabetic retinopathy. And I think there's a lot of potential for similar technology in cornea, particularly with diseases like trachoma. So, I think everything that I've talked about so far is, really exciting. There's a lot of potential to provide benefit to patients with these models that have been developed. But you might be wondering, where are all of these AI models? We have hundreds and hundreds of papers that have been published over the last 5 to 10 years describing AI models for various applications in cornea. But in practice, we have very few models that have actually been implemented. And I think there are a number of reasons for this. But several of the largest ones include this sort of black box phenomenon that I touched on earlier. So again, fundamentally, deep learning models are not very explainable. We don't have great techniques for interrogating how these models make their decisions. I mentioned the GradCam heat maps with convolutional neural networks, which can give you some indication of what portion of an image is most influential to a model's prediction. There is a fair amount of controversy around GradCam heat maps, though, and some people think that we are sort of conflating our own biases and when we interpret an image with what the model is actually doing. Newer AI architectures like the transformer architecture use something called an attention-based mechanism, which inherently actually lends itself to a bit more explainability because you can more directly interrogate exactly what the model is using to make its decisions. But we still have this issue of, again, multiple stacked layers that the inputs are being processed through. And so sometimes it could be, exactly what the model's paying attention to can actually be kind of lost in the shuffle. So this is still a major area that I think more research needs to be done to try and improve the explainability of these models. And particularly for medical applications, right? So, I mean, a lot of AI has been implemented in, social media and in the business world. But in general, I would say the stakes are quite a bit lower for those models, right? If they make a mistake, maybe someone loses some money or a social media user gets the wrong recommendation. But in our case, if an AI model makes a mistake, people go blind or they potentially die. So our threshold for models' performance is naturally a lot higher. And all of us went into medicine because we wanted to help people. So it's we all, I think, have a sort of like to take ownership of our of the care of our patients, and we have kind of a natural lack of trust for tools that we can't, directly interrogate exactly what information they're using to make their decisions. So again, I think this is an area that we need to make a lot of progress on before we can really implement these models on a large scale. Image quality also has a lot of impact on the performance of these computer vision models. Most of the time when we're training and evaluating these models, we're using, the ideal cases with perfect image quality. But of course, in the real world, image quality is quite variable. So we may not be getting a realistic representation of how a model would perform once it's actually implemented if we use those data sets. And along those lines, we, in general, often are not using representative data sets when we train and evaluate these models. Um, Most of the time we're using sort of a convenience sample from a single site or maybe a couple of different sites. But to train or develop AI models that are able to provide benefit to all populations, we need to train and evaluate those models uh, on subjects from all populations. I'll talk about that in a bit more detail momentarily. We also need to think a lot more about reimbursement mechanisms. It's still unclear how clinicians would be reimbursed if they use this type of technology. And being able to produce software and hardware at scale is typically going to require some kind of industry involvement. And industry, of course, they always need to know exactly what the potential profit margins are. So I think there are still a lot of regulatory hurdles, and the fine details still need to be worked out on exactly what the reimbursement model is for this type of technology when it's applied in the medical field. And then lastly, essentially all the most accurate and highest performing AI models to date have used a paradigm called supervised learning, which essentially means you provide the input, in our case, an image, and a label, which is the ground truth. So to take the example of keratoconus, you present the model with a tomography scan, and then you also tell it whether or not that patient had keratoconus. But the actual ground truth is often ambiguous in medicine, right? A lot of our diagnoses are made based on expert opinion or maybe an amalgamation of different tests, but none of those tests are perfectly sensitive or specific. Corneal ulcers are a great example, right? Cultures have quite good specificity, but very poor sensitivity. So oftentimes we'll have an eye that's obviously infected, but we don't have the ground truth data because nothing came back on the cultures. So coming up with ways to try and sort of modify the traditional supervised learning approach for medical applications, I think is going to be necessary for a lot of these use cases. And this just kind of gets back to that issue of lack of trust and lack of explainability in medicine. It's a pervasive issue, not just in ophthalmology or in cornea, but in medicine in general. And I think a lot more sort of advocacy needs to be done, and more robust testing of these models needs to be done before clinicians can be comfortable actually trusting what the model tells them. I mentioned a bit about image quality. There's a lot of good work going on to try and quantify this, but I think we need more studies looking at, exactly what aspects of image quality can be quantified, and how those impact the model's performance. As I said, once a model is implemented in the real world, it often will be exposed to examples of relatively limited quality. And it turns out you actually need examples of limited quality in your training set so that the model will learn to be able to sort of provide or extract some kind of meaningful information even from those lower quality images. So we need to be thinking about that when we're designing our training and testing sets for these computer vision models. And then this just kind of gets to that issue of generalizability and using representative data. So this is work that my group did that I think sort of demonstrates this principle. So to give you some background here, there's for performing binary classification of corneal ulcers. So again, taking an image and trying to predict whether or not it's a bacterial or a fungal ulcer. We had two separate data sets that we used to train and evaluate models. So one was called the MODERI data set, which was a prospective, consecutively collected data set of about 1,000 patients from Madurai in South India as part of the Aravind Eye Hospital. That were collected consecutively over the course of a calendar year. So sort of the best attempt at getting a representative data set of, if the model were to be implemented at this site over the course of a full year, what kind of cases would it be likely to be exposed to? And then the other data set was what we called the RCT data set. So data that were collected from multiple previously conducted randomized clinical trials, which were all, again, sort of conducted according to really strict inclusion and exclusion criteria, all had really high quality photographs, and were collected at the same site, but just under a different sort of data collection framework. So it turned out if you trained a model to do binary classification of corneal ulcers using that prospective data set, and then evaluated it on the prospective data set and the RCT data set, it performed pretty well in both cases. So that area under the curve was similar to what I described earlier, about 0.85, which is pretty good. And again, the important point is that it generalizes not just to the prospective representative data set, but also the more sort of contrived randomized clinical trial data set. Alternatively, if you train a model on that randomized clinical trial data set and test it on the randomized clinical trial data set, it performs fantastically. It's got an area under the ROC of about 0.95. So when we initially did this, we were really excited and high-fiving and thinking, okay, we've solved this problem. But then if you try to evaluate that model on the prospective representative data set, the performance drops off a cliff. The area under the ROC goes down to about 0.69. So this is just another example that if you are going to develop a model to be implemented in the real world, it's actually going to be used in patient care, it really has to be trained on data that's representative of the population and the types of cases that it's going to be exposed to in the real world. And to give you kind of a theoretical framework for why this is the case, if you take an image and feed it through a convolutional neural network, like what's depicted in the top right screen here, essentially what you're trying to do is approximate what's called a target function. So you can kind of think of theoretically out there in the world, there's this unknowable target function that produces the corneal ulcers that we end up seeing. So every corneal ulcer has a certain appearance to it, and every corneal ulcer is caused by a certain type of pathogen. So there's this, again, sort of hypothetical, theoretical target function out there that produces that association. And what we want to do is train a model that approximates that target function. And so we have these training examples. They're essentially just tuples of inputs and labels that we use to train our model that comes from this hypothesis set. We use some learning algorithm, take your pick of whichever one you like the most, and you come up with a final hypothesis, which is this convolutional neural network model that you've trained. But if we're approximating a target function that doesn't represent what's happening in the real world, then we're going to end up with a final model that is, again, approximating the wrong target function. So this, again, is why it's so crucial to have representative data that's not biased toward any particular population, not biased toward particular pathology, that's collected consecutively, and use that data to both train and evaluate the model to, again, ensure that it's generalizable and that we're not encoding bias in these models, which, again, we have really no way to effectively determine whether or not the models are biased because we can't directly see what information it's using to make its decisions. So this process really has to start from the beginning when you're developing your or collecting your training and your evaluation data sets. Again, we have to ensure that they're generalizable from the start because if they're not, there's no way to sort of recover a model that would be generalizable. So I kind of touched on a lot of these topics already, but just to sort of hammer the point home, I think future directions to try and move toward not just models that are published in the literature, but that are actually implemented and provide benefit to patients. I think we need to make a lot of progress in developing explainable AI models, and there's a lot of groups that are doing really great work in this area. We need to try and develop more diverse data repositories. So right now, a lot of our data sets are pretty siloed because it's difficult to share data between institutions. There are, patient privacy considerations. We also need to have what's called FAIR data, so findable, accessible, interoperable, and reusable data to be able to develop the data sets that are large enough to train generalizable AI models. And I mentioned the sort of institutional and site level limitations to collecting those data sets. There are also more logistical and data related issues, particularly formatting of data. A lot of the imaging software that we use in ophthalmology in general and in cornea specifically is not what's called DICOM compliant. So there's no sort of enforced standard to ensure that every manufacturer of imaging devices produces data that's formatted in a similar or interoperable way. A lot of these scans that we get are in proprietary data formats, and that makes it really difficult to try and collate data from multiple different devices or multiple different institutions. So I think trying to address that at the policy level would go a long way to allowing us to collect the size and diversity of data sets that we need. There's also this interesting concept called federated learning that I won't go into too much detail on, but essentially this allows you to train models from data at multiple different sites without ever actually having to share the data between the sites. So essentially each site trains its own model, and then the weights or the parameters of the models are averaged or combined in some way to come up with a sort of overarching model that indirectly has learned from all the different sites. And that might be a good way to try and address some of these patient privacy and data sharing limitations between different locations. And then, as I mentioned before, I think trying to develop alternatives to supervised learning, like weak supervision or self-supervision, to try and leverage, all the data that we have, not just the data that has a really reliable label, which again is not all that common in medicine. A lot of times there's a lot of ambiguity in those labels. So trying to come up with different strategies for how we actually train models, I think would go a long way to addressing these issues. And I think to sort of hammer the point home, we talked about some of the more technical aspects of AI in cornea, but I think if you want to make an impact in this area and try and close this implementation gap that I mentioned between models that are trained and published versus models that are actually implemented. Clinicians have a huge role in that, even if you have no real expertise in AI or machine learning, because what are the clinical questions that actually need to be answered. The workflow of taking care of patients and what type of technology would actually provide benefit and be feasible to implement within those workflows. So again, I would encourage everyone to, don't be shy about trying to get involved in this work. Being able to develop generalizable models that benefit patients requires not just machine learning engineers, but also public health experts, patients themselves and patient advocates, and clinicians. We all really need to have that interdisciplinary collaboration to be able to meaningfully provide benefit to clinical care in cornea. These are just a few of my acknowledgements for some of the work that I presented that my own lab has done. And I'm happy to provide references for anyone who's interested in doing some additional reading. And thanks so much. Feel free to reach out by email if you have questions or interest in collaborating. And all the code for the models that my own group developed is publicly available on GitHub.
Awesome. Thank you very much, Dr. Red. That was incredibly informative. I know I learned a ton, and I'm sure our audience did as well. We have some time for Q&A. So again, I would encourage anyone who would like to ask a question to use the Q&A panel within your Zoom application to do that. While we give people a chance to do that, I had a couple of questions. So of the kind of tools and applications, the uses that you talked about, which ones do you think have the potential to have the most transformative impact on improving corneal care in lower and middle income countries in the kind of near to medium term?
Yeah, I think that's a great question. It's certainly near and dear to my heart. So as I mentioned, my sort of main areas of focus are infectious keratitis and trachoma, which are the two most common causes of corneal blindness globally. So again, I'm a little bit biased because it's the area that I work in, but I think those two areas have a lot of potential to provide real benefit, and they're quite different sort of clinical implementation opportunities as well. So as I mentioned, the corneal ulcer question, there's a lot of great work being done in sort of biomarker quantification, disease progression, monitoring response to treatment. I talked a little bit about the sort of subclassification, more like augmentative implementation paradigms in corneal ulcers. But really, a lot of this is going to be done, I think, at the point of care in concert with clinicians. There's no real, autonomous implementations, at least that I see, for corneal ulcers specifically. Whereas trachoma, I think the main barrier to one of the main barriers to effectively eradicating trachoma, which we've been trying to do for many decades, is being able to conduct the large-scale screening campaigns that you need to determine which communities need mass distribution of macrolides. So I think an autonomous or automated implementation of AI in that situation would potentially really help us determine again where to target those MDA campaigns, and hopefully move closer to finally eradicating, what used to be, or for the vast majority of human history, was the most common cause of blindness in humans.
Yep, absolutely. Thank you for that. Another topic I'm really fascinated by is when you talked about the barriers, the lack of trust being a major barrier, and it seems like that cuts both within the professional medical community and also with the public, for whom these kind of tools are likely to become increasingly a part of their care. And obviously the explainable AI direction that you talked about is part of addressing that. What other thoughts do you have on kind of how those barriers of trust could be overcome?
Yeah, I think in general, machine learning engineers could probably do a better job of sort of explaining the results of their studies, right? So it's one thing to publish a study in the medical literature, but it's another to sort of communicate it to a lay audience, to someone who doesn't have the scientific background to know what an area under the RLC curve means. And I think, as I mentioned, the importance of actually testing these models in diverse representative data sets is crucial. And then if you're able to do that, being able to communicate that to the populations where the models will be implemented, right? So if you can go into a community and say, we have this cool new AI device that we want to use, and we've tested it, right here in your location, and here's how well it did. I think that goes a long way to sort of assuaging the concerns, not only of potential patients, but also, the clinicians that are managing those patients to say, okay, this actually probably does work in my population and can provide some benefit.
Yeah, absolutely. Always a key factor in building trust for any kind of public health intervention in the
Exactly.
community. So, all right, that's fantastic. I see no other open questions, so we'll go ahead and wrap up for this evening. Thank you so much again, Dr. Red, for sharing your time and expertise with us. Thank you everyone for joining us. Please remember to fill out the survey, the feedback survey that you'll be receiving on the completion of the webinar. And please do check out the future installments in our webinar series. Thanks again, everyone. Have a good evening.
Thanks, Colin. Thanks, everyone. Take care.
Bye now.